In video 2 of module 7, we're going to go over boundary layer equations, and we're going to use what we derived in part 1 and the ideas that we went over in part 1 to really now determine a working equation for laminar flow and a working equation for turbulent flow that we can use to solve problems. Okay, so up until now, we've been exploring how things were derived and how problems were solved initially in fluid mechanics for open flows. Now we're going to be looking a little bit more in detail as to how we can apply the equations that we've been looking at. And for this, we're going to come up with boundary layer equations that we can use for solving problems. Okay, so just for a little bit of background, in chapter 6, so in our previous module, module 6, for laminar flow, we had found an analytical solution for the flow. So we had found an analytical solution. And this analytical solution was the Poiseuille flow. Now, in this external flow, we actually do not have any analytical solutions. So for external flow, we can say we do not have them. We cannot come up with an analytical solution for any external flow around a body. Okay, and that makes it even worse because if we look at flow around simple shapes like a flat plate, we can sort of estimate what's happening through boundary layer theory. But if we don't have a flat plate or we don't have a slender body, it makes it even harder to approximate. So there's 3 different ways we can approach it. The first way is using boundary layer theory. And boundary layer theory is, once again, we can say it's only a prediction. The other way to approach it is to say, let's do some experimental results. Let's look at some experiments and find our solution experimentally. And that's usually the preferred method throughout history in order to find how a flow in an open flow with an object in an open flow would be found is through experimental testing. The third methodology, which can be used, is a numerical approach. And the numerical approach is using, for example, CFD, or computational fluid dynamics. Now, this is out of the scope of this class, but you might be faced with this in future classes as to apply computational fluid dynamics to a problem and looking at a finite element method to try to approximate the solution to a problem by simplifying the Navier-Stokes equations, for example. Okay, so there's 3 different methods, and the method that we're going to develop in this class is a method based on our laminar flow boundary layer theory and our turbulent flow boundary layer theory also. Okay, so we're going to use that. But before we get started with using that, in your book, you have a derivation of how the boundary layer equations would work in terms of continuity and momentum. So in your book, you have a derivation of the continuity and momentum along the wall in terms of the complex equations. If you apply then those equations to a flat plate, you then get some explicit solutions for your problem, or you get some approximate solutions for your problem. Okay, so we're going to go ahead and we won't do the full derivation. We're just going to write the result of the derivation of Prandtl's 2 boundary layer equations. But once we have those equations, we can then move forward and get solutions for laminar flow, for an exact solution for laminar flow, and an exact solution for turbulent flow as well. So we're going to start with laminar flow, but let's write down our equations in 2 dimensions essentially. So if we take a 2-dimensional plane, a 2-dimensional flow, and in this 2-dimensional flow, we're going to neglect gravity. And we're going to assume that the flow is similar in the 3rd dimension, okay? So in the depth dimension, it's going to be the same throughout. So if we look at just a portion of the flow in 2D, we can write that our continuity equation and momentum along the wall, so in our boundary layer, is going to be equal to the following. So the continuity is going to simplify to partial u partial x plus partial v partial y is equal to 0. Okay, we get rid of the z term. And for the momentum, and we're going to call this momentum along the wall, we have the following equation. We have u du dx plus v du dy is approximately equal to our free stream flow speed times du dx of our our uppercase U, okay, so our capital U, plus 1 over rho times d tau over dy. Now, we're not going to be using these equations directly. It would be very hard for us to use these equations directly and to solve for these equations. Now, we can see that in these equations, we've actually simplified our flow a lot by rearranging the equations around and getting rid of some terms, okay, compared to our full momentum equation, which can be written as our Navier-Stokes equation. Okay, this simplification is shown in your textbook. If you're interested, it's on page 458 and 457 of your textbook. Now, the tau value in these equations, just for your information, if we have laminar flow, so we'll write the laminar flow at the top, is just equal to mu du dy, okay, for laminar flow. That makes sense. We only have an effect in the y direction of viscosity that is happening. In turbulent flow, we have the mu term, but we have another term as well, and that term, we had actually derived it in our module 6 equations. So it's mu du dy minus rho times u prime v prime with a bar on top. So that's average u prime v prime, and this is for turbulent flow. And once again, you won't have to use these equations, but these are the basis for our flat plate boundary layer equations. So now that we have an equation for our laminar and turbulent flow, we know also that we have, so these are our equations, I'll box them in red. And we can also write that the boundaries of these equations, so to solve these equations, we need the boundaries, and we can say that at y is equal to 0, so if we look at a flat plate or a plate where this is happening, we can say that at y is equal to 0 at the wall, okay, we have that u is equal to 0 and v is equal to 0, okay? At y is equal to d as a function of x, okay, we know that in our system we have a boundary layer that starts to form as a delta. So y is equal to delta x. in the stream, so this is connected to the stream, we can say that our little u is equal to ux. Okay? So, doing some further derivations, we can then get values for laminar flow and find values for our turbulent flow. So we're going to start with the laminar flow flat plate boundary layer. So I'm going to write laminar flow flat plate boundary layer. So for laminar flow flat plate boundary layer, we can derive that our delta from these equations above, we can derive that delta over x is equal to 5.0 over Reynolds x to the 1/2. We had written that earlier and we had figured that out earlier, but here it's an actual exact solution that comes from the simplification that we made in our continuity and momentum equation. And this was developed by Blasius in 1908. Okay, so this is sometimes called the Blasius equation for laminar flow, but this is an exact solution. And this is the solution we're going to use for laminar flow. In the same way, our CF, or our coefficient of friction, is going to be equal to 0.664 divided by Reynolds x to the 1/2. Okay, so also derived from this. Okay, and we also can develop an equation for our displacement thickness. So if you remember, we have a term called displacement thickness, which is essentially how much the flow is displaced up as it moves forward into the flow. And this is a way of simplifying our computation. Our displacement thickness is d star over x is equal to 1.721 over Reynolds to the 1/2. So this tells us how much our flow has displaced upwards to keep our mass flow rate in check. Okay, now once we have these, we can go even further and come up with an equation that has our coefficient of drag. So from the coefficient of friction, we can actually find a coefficient of drag. And this coefficient of drag is going to be equal to the following. So again, this is derived in your book if you want to look at it, but our coefficient of drag is going to be equal to 2 times the drag as a function of L. Okay, so it's dl. Okay, so this is one term, okay, not to confuse it with d times L. And this is going to be divided by rho u squared times b times L. Okay, and we'll look at all these terms in a little bit. This is also equal to 1.328 over Reynolds L to the 1/2. So this is the coefficient of drag over the whole plate. Okay, so this would be for a whole laminar plate. So we can't find the coefficient, the Reynolds number halfway through the plate. It would be for the whole plate itself. Okay, and this is equal to 2 times CF which is our coefficient of friction. Okay, so what we can say, and this is also a function of L, okay? Our CF is a function of L. Okay, so what we can say is, from this equation, we can see that drag, or coefficient of drag, sorry, is equal to twice the skin friction coefficient. Okay, so that can be written out as what we have. Now, the DL here, the drag, is the drag on one side of the plate. Okay, so if flow is going on both sides, you would have to double the value. So drag is on one side of the plate. The equations work to compute for one side of the plate. Okay, that's very important. The other thing is that our B here, which we had written before, but let's write it again. Our B here is our thickness into the paper. And therefore, B times L, this whole term in orange, B times L is equivalent to the area of the flat plate. Okay, so this is equal to the area of the flat plate. Okay, so that gives us a little bit of what equations we can assume to have for solving our problems. And all of these equations in this image right here can be used to solve our problems. So for laminar flow, obviously. Okay, so let's do a quick example of how we can apply these equations and try to understand what's happening. So I'm going to copy over an example. So it's example 7.3 in your book, and it says a sharp flat plate with L is equal to 50 centimeters and B is equal to 3 meters, so thickness into the paper, is parallel to a stream with a velocity of 2.5 meters per second. So we know that we have a flat plate, okay, and we can draw this flat plate. And we know that we have flow coming in at 2.5 meters per second. We know the flat plate is 50 centimeters long, and we know that into the paper it's 3 meters wide, essentially. Okay? We're told to find the drag on one side of the plate. So we're not going to be interested in the bottom side of the plate. We're only going to be interested in the top side of the plate, for example. Okay? We're going to look at only one side. Okay? And it says to find the drag on one side and the boundary thickness at the trailing edge for air and water at 20 degrees and 1 atmosphere. So one time we're going to have air going at 2.5 meters per second, and then we're going to have water going at 2.5 meters per second. Okay, so if we sort of draw what's happening and a little bit of the different points on our system, the first thing we can say is that this point at the front here is called the leading edge. And at the back of our plate, we have our trailing edge. Okay, so when it asks for the values at our trailing edge, we know where to look for. We need to find the boundary layer thickness at that point. Okay, so our boundary layer, we can draw it and we can exaggerate it. It's going to look something like this. I'm going to draw it in green. It's going to look something like this. We're going to have a growing boundary layer as we go, and it's going to grow more and more and more. Okay, and eventually it's going to reach this height, and throughout it's going to reach a height, and this height is going to be a function of x. So we can say that x starts here and goes towards the right. Okay, but we know obviously that the boundary layer thickness at the end is going to be the boundary layer thickness at L. So let's try and solve the problem. Okay, so for part A, we're going to use air. So for air, how do we solve our drag on one side of the plate? So in order to find the drag on one side of the plate, we're going to have to find our, we're going to use our equation CD for CD. Okay, so we're going to try and find our, we're going to use this equation for CD. And if we can find CD, then we can find the drag. Okay, we have three different ways of finding CD. We can either find CD with this, or we can find it with this, and then we can finally find the drag from the equation on the left. So the first thing we need in order to find anything is always the Reynolds number. And the reason we need the Reynolds number is because we need to be able to say if it's a laminar flow, or if it's a turbulent flow, or if it's a transition flow. Okay, so we also know that for open flows like we have here, Reynolds of L, or Reynolds of X, has to be less than 5 times 10 to the 5 to be laminar usually. Okay, that's our transition. Okay, and we can usually say that if you remember the rule 2,500 to Reynolds to 10 to the 6, we're going to assume that we have laminar. And turbulent is going to happen above 10 to the 6. Okay, so let's try and find our, and usually, so we go up to 10 to the 6 and we can use laminar, but our transition usually occurs at 5 times 10 to the 5. So this should be, transition is equal to 5 times 10 to the 5. Now let's calculate our Reynolds number. So our Reynolds number at the interest point, which is our trailing edge, is equal to U times L. Okay, that's our distance, so it would be U times X, but in this case, it's U times L because we're using L over our kinematic viscosity. And for air, we need to find our kinematic viscosity. So what we're going to do is we have L, we have U, we just need to find our viscosity. So for our viscosity, we can go to our table and we can look for air at 1 atmosphere. And we know that the air is at 20 degrees, so we can use the values in this table right here in table A4. And from table A4, we find that for air, we have a value of 1.49 times 10 to the minus 5 at 20 degrees. Okay, we're going to use dry air. We can also, if we have another, if we need more for different temperatures, you could use a different table, such as table A6, for example, where there's a little bit more detail, and find it this way. But here we're going to use table A4, and it makes it pretty simple to find what we have. So we're going to write that our equation, so our viscosity is going to be equal to 1.5 times 10 to the, 1.49 times 10 to the minus 5. And we know that our length is equal to 0.5 meters. So if we plug in the values, we have Reynolds L is equal to 2.5 times 0.5 over 1.49 times 10 to the minus 5. And we get that this value is 83,300 for Reynolds. And so we know that our value is lower than 5 times 10 to the 5. Okay, it's lower than 5 times 10 to the 5, so we can say that we have laminar flow. Okay, so that secures us in the sense that we know what our laminar flow is. Now, in order to find the drag for one side, we're going to have to use the coefficient of drag equation. So we know that coefficient of drag is equal to 1.328 over Reynolds L, in this case, to the 1/2. And it's also equal to the drag, so it's 2 times the drag divided by rho u squared BL. And we can verify this from our equations. We have 2 times the drag as a function of L over rho u squared BL from these equations up written here. So we have this, and from here, we're going to be able to find our CD from the Reynolds, and then eventually find our drag. So I like to do it in steps. I like to find CD first, and then find the drag of one side first, but it's up to you if you want to do it all at once. So our CD is going to be equal to, if you compute it with Reynolds number, is going to be equal to 0.0046. And our drag for one side, we remember that the drag written is for one side, so we don't need to double it, is equal to CD times rho over 2 times u squared times BL. And so we need our density of air as well. So density of air can be found from our charts once again. And so if we go to our air, we can find the density. So we can go to air at 1 atmosphere. We can find its density at 20 degrees. So we can see that at 20 degrees, we have a density of 1.2. And we could have used this table too with 1.5 times 10 to the minus 5. We can see there's very little difference between 1.49 and 1.5, but we could have used this table that has a little bit more information on air, and it's not dry air. That's why there's a slight difference in values. So you could have used 1.5 or 1.49. It's not a big difference, okay? So we have 1.2 for the density, so kilograms per meters cubed. So we can plug in our 1.2 in our equation, and we get that the drag on one side would be equal to 0.026 newtons. And so I'm just going to write here where we wrote our V. This is from table A4. And from table A2, we would have had V is equal to 1.5 times 10 to the minus 5. They're both valid possibilities to use. Okay, so moving forward, we have found our drag for one side. So now the next thing we have to do is find our boundary layer thickness. Boundary layer thickness. And that's our value for delta. So we can say that delta over L, because that's our distance for X now, is equal to 5 over Reynolds L to the 1/2. And if we plug in the values, we get that this is equal to 0.0173. And don't forget to do this step. Sometimes we forget to do this step, is to move the L to the other side to find just delta by itself. And so delta would be equal to 0.0087 meters. Okay, for water in part B, you would repeat the same procedure. So you would repeat the exact same procedure as with air. So you would find your values in your tables in your appendix, and you would look for all your values in exactly the same way. Okay, so, and you would see that for water, there's a little bit of a different aspect to it because the Reynolds number is actually very close to transition. So the flow might be turbulent for water. But if you want to look at how you would repeat the procedure, just do the same procedure with water and you would find your Reynolds number again and see that your Reynolds number would actually be possibly turbulent. So there might be a problem with the water solution. Okay? And I'll let you do that in your own time. Now, what we can find from this first simple experiment is that in part A, we found that delta is equal to 0.0087 meters. So what that means is after 50 centimeters of flow over a plate, the boundary layer has increased by 8.7 millimeters. Okay, our boundary layer is 8.7 millimeters thick. So it's actually very small when you think about it. Okay, so it gives you an idea of how big the boundary layer is for the system itself. Okay, so for water, you would just repeat the procedure and you would see that maybe you would have to use other equations than your laminar equations, but the idea here was just to practice your laminar equations. So you can see in your, you can look at the solutions for example 7.3 in your textbook and see what they would get for water as a whole. But essentially for water, you would get your delta would be equal to 0.0022 meters, and you would get that the drag is equal to 5.6 newtons. So you can double check those numbers. Okay, so the next thing we're going to go over is our turbulent flow. So we're going to switch gears to now look at turbulent flow and analyze what we have in terms of turbulent flow. So for turbulent flow, we can say, the first thing we can say is that turbulent profiles are not parabolic at all. And what we mean by that is that our flow against the plate does not look like a perfect parabolic shape. Okay, we actually have some very big fluctuations in what happens in our flow. And in order to solve for this, we're going to have to use our knowledge from Module 6 to derive all the useful relations. So remember in Module 6, we used the logarithmic laws, and we're going to do the same thing here. So we're going to use the logarithmic laws from Module 6 or Chapter 6 for pipe flow, and we're going to derive some useful relations. For flat plate flow once again. And these relations are not, they're not exact solutions, but they are solved through the laws of logarithms, and in the end we can use them as exact solution essentially. So for our turbulent flow, we get that delta over x can be approximated by 0.16 over Reynolds x to the power of 1/7. And CF is equal to 0.027 over Reynolds x to the 1/7. If you're interested in the derivations, once again, you can use your textbook and see in your textbook the whole derivations of this. Even the textbook doesn't go fully into the derivations, but it does go into more depth than what we have in the lectures. Since we're more interested in the use of the equations than the actual derivation, this is why we're going a little bit faster. We've also derived this in detail in Module 6 with the logarithmic laws, so we would have to go through the same kind of procedure again as in Module 6, which we don't really have to because we hopefully understand the flow. Now, our coefficient of drag for our turbulent flat plate flow is not double of the skin friction drag. It's actually only a little bit higher. The coefficient of drag is equal to 0.31 over Reynolds x to the power of 1/7. And so we have that this is actually equal to 7/6 of CF as a function of L. Okay, so we can say that for a turbulent flat plate, the coefficient of drag, and I'll write for a turbulent flat plate, is 16% more than CF. So it's not double CF as it was in our laminar flow. Now, going further than this, we can also say that tau at the wall, if we're interested in finding tau at the wall for turbulent flow, we can say that it is equal to 0.01135 times mu to the 1/7. And let me write the 7 a little bit better so that it is clear. Mu to the 1/7 times rho to the 6/7 times u to the 13/7 over x to the 1/7. Now, what is very interesting in the turbulent flow methodology is that since we don't have some analytical solutions, we're going to be using the same type of analysis that we have in the past for turbulent. So remember, in our turbulent flow, we had some Moody charts for our flow inside pipes. Well, we're going to have another chart here, which is the flat plate analog for a Moody diagram. So it's exactly the same thing as a Moody diagram, but for flat plates. And we're going to copy it over. In your book, it's figure 7.6. So I'm going to copy over figure 7.6, which is shown right here. And figure 7.6 is a way to solve the problem without having to use equations to essentially solve for any value, and can be used in exactly the same way as the Moody chart. Okay, so if we look at this graph here, we have on the left side our CD, on the bottom our Reynolds L, and we have the same effect with our rough pipes and our smooth pipes. So we can see that if we have laminar flow, we follow this type of line. We follow an equation that is very simple. And this is equation 727 in your textbook. This is the equation that relates our coefficient of drag to our drag. Okay, it's just a simple equation that says CD is equal to 1.328 over Reynolds to the 1/2, which is equal to 2D over rho u squared BL. Okay, so this equation is accounted for. Now, for our transition region, we have a little bit of a more complicated region. We actually have a region that is bound in our transition. So we don't have it before where we had a simple transition and the transition would change. We actually have an area where the transition could happen. And depending on the flow, sometimes you'll have that transition and sometimes you won't. Okay, And this transition uses two different equations for two different values for the transition, for the Reynolds of transition. But what we can know is that transition will always occur between this leftmost point here, okay, this leftmost point here, which is 5 times 10 to the 5, and our rightmost point, which is somewhere here. Now, in general, we say that the start of transition occurs between this point and this point. So it occurs between this point right here, 1, and this point right here, 0.2. Okay, and this 0.2 is thought to be at 3 times 10 to the 6. And so what we have is we actually have an equation that gives us the shape of the line going from here to here at 1, and we have another equation that goes and gives us the line from here to there. And those two equations, I'm going to copy them over so we don't have to write them down, but the equations are the following. So the equations are going to go right here to the right of the graph, and we have that the equation is essentially, we have an equation for 5 times 10 to the 5, where transition would start happening at 5 times 10 to the 5, and then another equation where transition would happen at 3 times 10 to the 6. And we can see that the base of the equation is the same as our fully turbulent flow minus a constant in terms of Reynolds that would account for this transition phase. And again, this is much of an approximation. And if you're not given the transition place of your flow, or if you don't know where your flow is exactly, you would have to guess which one to use. Okay, so if your flow is between 5 times 10 to the 5 and 3 times 10 to the 6, you know that you have to use your transition equations, which are shown here, or you can use your chart and just find a point either between 5 times 10 to the 5 and 3 times 10 to the 6. So we're going to do an example problem where we are told what our Reynolds transition is, so we can it'll help us out in finding what is happening, and we know what to use as an equation in order to solve for the problem. Okay, so we're going to do a specific example where we have that given to us. Okay, and what will be given to us is actually the transition value as well. Okay, so knowing that, this equation, these two equations will help us solve the problems if we have to account for some correction factor, essentially. Okay. In addition to this, in pipe flows, just to finish our discussion of this chart, we know that in pipe flows we have E over D is our value for roughness, and this is the roughness coefficient, essentially, which is a dimensionless coefficient. In this case, in flat plate, we have L over E, so slightly different. Since we're using length as our characteristic length, this is for our flat plate definition of our roughness. Okay, so we can go ahead and try to do an example with this problem. So we're going to do an example, so I'm going to copy it over. We have that a hydrofoil that is 50 centimeters long and 4 meters wide moves at 28 knots. Okay, so this is knots. Okay, so we'll look at that in a second. In seawater at 20 degrees. Using flat plate theory with Reynolds TR is equal to 5 times 10 to the 5, so Reynolds transition. Estimate its drag in newtons for a smooth wall and for a rough wall with E is equal to 0.3 millimeters. Okay, so we're going to do two different problems. And we know that our Reynolds transition is equal to 5 times 10 to the 5. Okay, so that's something that we know. And the first thing we're going to do is, since we know our Reynolds transition is 5 times 10 to the 5, that means that above 5 times 10 to the 5, we're going to have turbulent flow. And below 5 times 10 to the 5, we're going to have turbulent flow. Okay, so that's really important. So we can write that we're going to start with our smooth wall. And the first thing we're going to do is we're going to find our Reynolds number for our seawater on a smooth pipe. So we have that Reynolds, we know that Reynolds of L is equal to rho times velocity times L over mu. Okay, we're going to use a full equation now because we're looking at seawater. And if we go to our tables, we need to find rho and we need to find mu for seawater. So going to our tables, we're going to be able to find our rho and our, from table A3, we're going to be able to look at seawater and find our rho and our mu. So our rho and our mu are right here. So we have 1025 and we have 1.07 times 10 to the minus 3. Okay, so those are our two values that we're going to use. So going back to here, I'm going to write that rho is equal to 1025 and mu is equal to 0.00107. Okay, the other thing we need to know is what knots convert to. So 28 knots is actually equal to 14.4 meters per second. So you would have to look that up in terms of to be able to convert it. Now, once we have that, we can say that Reynolds L is equal to 1025 times 14.4 times 0.5. That's our value for the length of the hydrofoil divided by 0.00107. Okay, so we can think of our hydrofoil as a flat plate inside the water with water rushing around it at the speed of 14.4 meters per second. And our hydrofoil is 50 centimeters long, so the leading edge to the trailing edge of our hydrofoil would be 50 centimeters, and we know it's 4 meters wide. So we can find that our Reynolds number is actually equal to 6.9 times 10 to the power of 6. So that means we have turbulent flow. So if we have turbulent flow, we can say that for our smooth pipe, we can use our equations to find the drag. So our question now is, what equation for coefficient of drag are we going to use? So we saw that when we have turbulent flow, we had an equation that said that coefficient of drag is equal to 0.031 over Reynolds to the 1/7. Okay, so we had that equation. Now, in our problem, we're given that we have a Reynolds transition of 5 times 10 to the 5. And if we look at our problem and we look at what we have, we're actually going to have to look at our chart and see, can we use this equation? Or should we use our equation that says CD is equal to 0.031 over Reynolds to the 1/7 minus 1440 over Reynolds L. Which one should we use? Well, since we have our transition starting at 5 times 10 to the 5, we have to look up until where the transition occurs. So we actually have to look in our chart whether the transition occurs. So we're going to make a choice between this equation or this equation. And we have to, in order to do that, we have to look at where our transition ends in our chart. So if we follow the line in our chart, so let me erase all this. We know that this is 5 times 10 to the 5 is this line right here. We see that our transition phase could end all the way to 8 times 10 to the 7. So we have this whole transition phase where the transition starts here, but could end all the way here. And what the equations on the right do, these two equations on the right, they essentially give us a correction factor for if you are still possibly in the transition phase. Okay, so up until our value of 8 times 10 to the 7, so we can say between 5 times 10 to the 5 and Reynolds of 8 times 10 to the 7, if we know the start of our transition, we have to use the equations that are given above. So we are still in that phase, so we have to use the equations above to correct our value for fully turbulent flow, which would be above that. And this is especially true for this is true because we have a smooth pipe. Okay, as soon as we don't have a smooth pipe anymore, the transition is usually not taken into account. Okay, so it's a little bit of a complex thing to understand, but it does make sense if you think about it. Okay, we have a smooth pipe, therefore our value could still be in the transition region with our smooth pipe. Okay, so we're gonna essentially say that our coefficient of drag that we're gonna use is this equation right here. We have to use the correction for the fact that we could still be in the transition region. So if we use this equation and we plug in our Reynolds number, and I'll add the sub-L here, we actually get that our CD is equal to 0.00306. Okay, and this takes into account that the start of our plate flow is still possibly in transition, and therefore we can't assume that it's fully turbulent at 6.9 times 10 to the 6. Okay, now our drag can be found from CD, so we have that drag is equal to CD times rho over 2 times U squared times BL, and we are not told whether or not to find the drag on one side or both sides, but since the hydrofoil is submerged underwater, we're going to multiply by 2 for the two sides. So we're going to say we're going to multiply by 2 to get the two sides. So we have the 0.00306 multiplied by 1025 over 2 multiplied by 14.4 squared times 4 times 0.5 times 2 turns out to be equal, so the drag on the hydrofoil turns out to be equal to 1,300 newtons. Okay, so we have this value. Now, in part B, we're gonna focus on the rough plate, as if we had a rough plate. So if we have a rough plate, we can say that for the rough plate, we have an L over E of 500 over 0.3. Okay, and this is equal to 1667. Now that we have a rough plate, we know that we are not going to be in this transition region. We have to follow a curve of our effect of roughness. And our effect of roughness is actually very, very extreme on plates. So here, we are not gonna use an equation. We cannot find the coefficient of drag through an equation. So CD would not be found through an equation because we have a rough wall. And if we look at figure 7.6, we'll see why. So in figure 7.6, we can see that our value of L over epsilon is equal to 1667. So that means that our value is somewhere here. Okay, so it's somewhere here and it follows this line, this curvature here. As you can see, it's not even close to our transition region. Okay, our smooth pipe, however, initially was on this line. And let me just rewrite that, was on this line here. And since it was on this line here, we had the potential of it being in transition, which is why in part A we used the equation. We could have also in part A found our CD to be 0.03 by just plugging in our values and finding that it was going to be somewhere in this region right here. But we couldn't know that, so we used the equation instead. Okay, now in part B, we have a rough wall, and we can see that as soon as you have a rough wall and the value is low for that L over epsilon, we see that we're much higher than the transition region. So the roughness actually has a very big effect on the flow. And using figure 7.6, we can now find our CD directly from figure 7.6. So we can say that CD at the Reynolds number that we have, so our Reynolds number in our question that we calculated is 6.9 times 10 to the 6. So somewhere around here. And we can see that our CD would be somewhere around there. Okay, this is approximate once again. And we can say that this would probably be 0.0075. Okay, so 0.0075. If we zoom in, you can sort of see that that would be the value because 0.07 is going to be 0.007 would be somewhere here. Okay, so we're going to assume that we have an approximate CD of 0.0075. So we have CD is approximately equal to 0.0075. And from there, we can find that our drag from the equation, same equation as before, we can say that our drag would be equal to something like 3,186.3 newtons. Now, there's another methodology that we can use too. We can use an equation to solve for this if we wanted to. So there's also an equation that mimics the chart. So just like the Holland equation in our pipe flow, we also have a set of equations that we can use for our flow on flat plates. And this equation follows. So it's equation 748 in your book, and it's 748b in your book. There's also an A equation that finds for CF, but CD is said to be essentially equal to 1.89 plus 1.62 times log of L over epsilon to the power of minus 2.5. And if you solve for this equation with our values, you would get a CD that's equal to, so this is an equation, we'll circle it in. So you can use this equation if you don't want to use a chart, okay, for any turbulent flow. So it has to be a turbulent rough plate flow. So this is for rough plate flow. We could use this equation and find that we get 0.00742, which would yield a drag value of approximately 3,150 newtons. Again, these are all approximations, okay? Turbulent flow is not easy to approximate, but we can see that the drag increased drastically between a smooth wall where we had a drag of 1,300 at the top here, and a drag of 3,200 nearly for our drag on a rough surface. Okay, so that's very important to understand. Okay, so again, the suggested technique that I would give you is to always use your chart to visualize what's happening. Okay, it's much easier to use a chart to see what's happening and what you're dealing with than to use equations that you can't use visually. Okay, and you can use your charts for solving problems. You don't have to use your equations, and you don't have to get the exact same values as in the solutions in your book. Okay, but clearly we can see that from our charts in part A, since we had a smooth surface and we knew that we were still close to our transition phase, so we were still very close to this transition phase, we had to use our equation 749, or our equations shown here. So this is equation 749 to solve for a value. And we were given that Reynolds transition was 5 times 10 to the 5, and our Reynolds number was 6.9 times 10 to the 6, which was still close and within a range where we had to use this equation. The range is specified here. So this is the range where this equation should be used to take into account the fact that the flow at the start of the leading edge could still be in transition. Okay? Once you know that, you use this equation and you can find CD and then drag. Okay? You could have also guessed CD within that region, within the transition region, or on the smooth flat plate region, but you would have gotten a result that might have been a little bit different from the chart. You don't have a specific line to follow since the transition region is sort of an area, okay? And then in part B, because the plate was rough, then it made it a lot easier to solve for, in the sense that we have a rough pipe, therefore we are outside of this transition region, especially if you have a low number for your L over E, and we could solve it directly from our chart. The other solution was to use equation 7.48b, which we wrote down at the end of the question as well. So this concludes video 2 of module 7, and in video 3 of module 7, we're going to introduce experimental flows a little bit, just so we understand on high level what is happening with experimental flows.